Welcome to Chapter 7, File Handling and Programming. By the end of this chapter, you'll define and classify computer files, explain the data hierarchy structure, perform basic file operations, apply control break logic in programming, merge and update files effectively, and compare sequential and random file access. Text files store human-readable content, a plain .txt readme, a .csv file of tabular data like an exported spreadsheet, or an HTML web page structured with tags. Binary files instead store data encoded in a format meant for machines, not people. A compiled .exe program ready to run, an image file like .jpg or .png, or audio and video files like MP3 and MP4, compressed in binary for playback. Here's that text versus binary distinction shown visually, side by side. Text files stay human-readable and editable in any plain text editor, while binary files require the right program or codec to interpret their encoded format correctly. Data builds up in 5 layers. Characters, letters, numbers, symbols are the smallest unit. Characters combine into fields, a single attribute like a name or age. Fields combine into records, describing one complete entity, like an employee with a name, ID, and salary. Records combine into files, like a payroll file, holding every employee's record. And files organize into a database, a structured system managing many files together, like a CRM, tracking contacts, orders, and support cases. A good file name is descriptive. January payroll instead of file 1 avoids special characters like slashes or asterisks, and follows a consistent naming convention like camel case or snake underscore case. The file name extension, the suffix after the period, tells the OS and applications how to handle the file, .txt, .csv, and JSON for text, .jpg, .png, and .gif for images, .docx, .pdf, and XLSX for documents, letting you identify a file's type at a glance. File organization is how files get stored and arranged for efficient access. Folders or directories are logical containers grouping related files together. A file path specifies exactly where a file lives. An absolute path starts from the root directory, like C users documents report.docx, while a relative path is based on wherever you currently are, like .documents report.docx. Best practice: organize into meaningful folder structures, like projects, /2024, January, and avoid clutter by archiving old files or using cloud storage. Declaring a file means specifying its type, text or binary, and reserving a variable to reference it throughout your program. In Java, that's a file, buffered reader, or buffered writer object. In Python, it's as simple as a plain variable holding the file object. And in C++, you'd use a file stream object, ofstream for output, ifstream for input, or fstream for both. Opening a file links your declared variable to the actual file on disk and specifies the mode. Read mode opens an existing file to pull data from it, while write mode creates a new file or overwrites an existing one. From there, reading operations fetch data, line by line, in chunks, or all at once, while writing operations send formatted or raw data out, with error checking to confirm it actually wrote correctly. Closing a file matters more than it might seem. It flushes any buffered data that hasn't been written yet, guaranteeing every write actually gets saved, and it releases the system resources the file was using. Best practice: always close files explicitly, or use a language construct that handles closure automatically, since skipping this step risks data corruption. Here's basic file writing and reading as actual C++ code. An ofstream opens the file in write mode and writes a line of text, then closes. An ifstream reopens the same file in read mode and pulls that line back out with getLine. Notice both operations check is _open. First, handling the error case if the file couldn't be accessed. Here's that same pattern in Java. A file writer wrapped in a buffered writer handles writing a line of text, then closes. A file reader wrapped in a buffered reader reads it back line by line in a while loop, continuing until readLine returns null, signaling the end of the file. And here's the same read and write pattern in Python, by far the simplest of the three. Open, in write mode, write your text, close. Then open, again in read mode, call read, to grab everything at once and close. Python's built-in file handling trims away most of the setup the other two languages require. Control break logic is a technique for processing and summarizing grouped data in sequential files. It executes specific actions whenever there's a break, a change in some control field's value, like moving from one category to the next. Common uses: generating subtotals for grouped data, like sales totals by region, or producing formatted reports with headers and footers separating each group. Implementing control break logic follows 4 steps. Initialize variables to track the current group and its running totals. Detect a break by comparing the current record's control field to the previous record's value. Handle the break by outputting a summary and resetting your variables for the next group. And keep processing data until the entire dataset is done, making sure that very last group still gets handled properly at the end. Picture a real example. You need a report summarizing total sales by region, with the data file already sorted by region. As you move through the file, you calculate and display each region's total before moving on to the next. And that's control break logic in action, using the region field itself as your control breakpoint. Walking through it step by step, initialize current region as empty and total sales at 0. As you read each record, detect a break by checking whether its region differs from current region. When it does, handle the break. Output the total for the region you just finished, reset total sales to 0, and update current region to the new one. Otherwise, just add the sale to the running total. And at the very end of the file, don't forget to output that final group's total too. Here's control break logic as actual Java code, tracking sales by region. As the loop moves through each record, it checks whether the region changed from current region. If so, it prints the previous region's total and resets before continuing. The sale amount always gets added to the running total, and the loop prints one final total after it finishes, capturing that last region. Here's that same control break logic in C++. Identical structure, checking for a change in region, printing and resetting on a break, accumulating sales otherwise, and printing one final total once the loop completes to catch the last group. And here's the same control break pattern in Python. The loop checks each record's region against current_region, prints and resets whenever a break is detected, and accumulates sales the rest of the time, with print statements after the loop, and inside it working exactly like the Java and C++ versions. File merging combines two or more files into a single output file, with every record organized in logical order based on a shared key. The purpose: creating one unified file out of multiple sorted files, making later processing or reporting far simpler, while keeping the data consistent across whatever analysis or manipulation comes next. Merging files properly requires two conditions. Same record layout. Every file being merged must share identical fields, data types, and structure. So if one has employee ID, name, and salary, the others need that exact same structure. And sorted in the same order, every file must already be sorted on the same key, like employee ID or date, since that's what lets the merge process run efficiently using simple sequential comparison. Picture two sorted employee files, one from Division A, one from Division B, both sorted by employee ID, merged into a single file, still sorted by employee ID, containing everyone. Or picture monthly sales files from January, February, and March, combined into one file sorted by transaction date. Same underlying merge logic, different real-world data. Merging follows 5 steps. Open all the input files for reading, plus the output file for writing. Initialize pointers tracking the current record in each input file. Compare the key field, like employee ID, across those current records. Write whichever is smaller to the output, and advance only that file's pointer. Once one file runs out, handle the remaining records by appending everything left in the other file. And close every file at the end to guarantee data integrity. Here's a concrete merge example. Division A.txt holds employees 101 and 103. Division B.txt holds 102 and 104. Merging them by employee ID produces merged employees.txt, with all 4 records in proper numeric order: 101, 102, 103, 104, exactly demonstrating why both files needed to already be sorted before the merge could work this simply. Here's that merge process as actual Java code. 2 buffered readers track a line from each input file, comparing them with compare2 to decide which gets written first. Once either file runs dry, the remaining while loops flush whatever's left from the other file straight to the output, exactly matching the 5 merge steps we just covered. Here's the same merge logic in C++, using ifstream and ofstream. The core while loop compares line A and line B directly with C++ string comparison operators, writing the smaller one and advancing that file. Then 2 more while loops drain whatever's left once one file hits EOF off. And here's the identical merge pattern in Python. Open 3 files, read the first line from each, then loop comparing line A and line B directly, writing the smaller and reading the next line from that file, followed by 2 more while loops flushing any remaining lines once one file runs out. Master files, also called primary files, serve as the main, permanent storage of data: employee records, product inventories, things meant to persist. Transaction files are temporary, storing just the updates or changes: daily sales, new hires, account adjustments. You can update the master 2 ways: directly modifying it in place, or creating an updated copy by merging the master with the transaction file to produce a new version. Throughout the day, transactions like customer orders or inventory changes get recorded into a temporary transaction file rather than updating the master file directly. Direct updates for every single transaction would be slow and risk corruption from constant access. The transaction file captures everything in real time without touching the master at all. At the end of the day, merging the transaction file into the master brings the permanent records up to date. And if something goes wrong during the day, the master stays intact, with the transaction file itself serving as a backup of everything that happened. This transaction and master approach pays off in 3 ways. Speed. Transactions record fast in real time without constantly interrupting the master file. Data integrity. The master only gets touched once, at the merge, which sharply reduces the risk of errors. And efficiency. Processing all of a day's changes in one bulk merge ensures the master ends up accurate and fully consolidated. Sequential files get read start to finish in the order they're stored, ideal for linear processing and best suited to batch jobs like payroll or report generation. Random or direct access files let you jump straight to any record without reading through the others first, ideal for real-time applications like databases needing immediate lookups. Sequential wins for large datasets, logs, and archives. Random wins whenever you need a quick, specific lookup, like customer or inventory management. No new assignment this time. Just make sure your Canvas assignments are complete, and bring yourself to class ready to learn. We'll be building directly on file handling, control break logic, and merging as we keep moving forward.